in this book that does a geometric interpretation or geometric version of various algebraic identities that we probably by now take for granted, seeing as most of us have been students for, well, some time ago. The first one is really the distributive law for addition and multiplication. So book 2, hence it's called Fundamentals of Geometric Algebra. I haven't looked past propositions 4. So, but as far as I've seen, most of the first 4 propositions are of this nature. There are also 2 definitions at the beginning of the book, which I think we can leave for another day. Definition 1 is really just an obtuse way of defining a rectangle, which we've kind of been using. We've been talking about squares, maybe not rectangles per se, but definition 2 is something that will come up in definition 4. So I'm going to leave that till we get to definition 4. And I learned a new word actually when I looked at definition 2, but I'll leave that for Dan to talk to you guys about. Okay, so proposition 1. So this is the geometric version. Yeah, I never knew this. Okay, so the distributive law it just says that A, B plus C plus D. The way they do it, they just put some dots here. This is probably not how we would write it. A little bit loose with the infinities there, or not infinities, certainly not. I usually don't do this with an infinite number of terms, but arbitrary number of terms. So, as I said last time, when I present these propositions, I'm gonna kind of do away with some of the verbosity of Euclid. He kind of does things in a way where he doesn't refer to any variables. It's just natural language. But I think these are probably cleaner, easier to understand if you just kind of label everything with letters. So I think I'll do that from now on. So the proposition says it's a geometric version of this. I'm going to let BC be a line segment, I guess, and D, E, B points on the line BC. I think in Euclid, he says D and E are randomly chosen on BC. And I think we kind of had this discussion last season about random numbers of points on how to choose random points on the line. But I think we're just going to say they're arbitrary points and not worry about what random means. We'll let A be another line. I'm not a huge fan of this notation. Usually these capital letters are referring to points, but I'll stick with this for now and just note that A is really another line segment with a predetermined length, right? And it's really the length of A that we'll be using here. Okay, and we're going to consider the rectangle. I'm going to introduce some notation here. Remember, a rectangle here is just a parallelogram with a right angle, and a parallelogram is shape cut up by two sets of bounded by two sets of parallel lines. And yeah, I mean, obviously you want them to intersect, not parallel lines that are just kind of on top of each other. So a rectangle, I'm going to say RBC, right? Bounded by BC and A, right? So really, we want something like a line, which is like this. This is BC. I forgot again to go back to pen mode, BC. And we want this to be A, right? And we want a little right angle here. Right, so this thing here we'll call A. Okay, and the rectangle, obviously, what I mean is this rectangle here. Just complete it. Right, obviously, a rectangle is bounded by 4 sides, not 2, but there we go. Okay, so similarly, most of these propositions is really just notation and saying things in a way that that's not super confusing. So, the claim here is that RBC is equal to RBD plus RDE plus REC. Probably should draw these in. So we said that D and E were points on BC. So there's a D and there's an E, right? And this equation here that I've written is really about the areas of the rectangles. And RBD is a rectangle formed from the line segment BD and A as the other side. Similarly, RDE is the rectangle formed from DE and A on the other side, and similarly with EC. And we can already see what we're going to do. There's some constructions we have to make before we write down the proof. And the proof is really just observation that the big triangle is made up from the smaller triangles. So right.
Maybe it's worth, just in terms of reading Euclid, I agree with what you're saying about how we present it, but when the language diverges from what's in the book, it means that this maybe we're not assisting somebody in being able to read the book. So I'll just make one comment that this somewhat strange construction of a rectangle contained by 2 straight lines, which sounds to our ears ridiculous because you need 4 straight lines to contain a rectangle, but he means like something like the product of the 2 lines, right? You take the 2 lines, put them at a right angle, and then form the rectangle like you've done here.
Right. Yeah, that was when I was reading it, that confused me a little bit, but I'm like, that's the only thing that it can possibly be, right? So that's what I mean in the picture as well as I've written. But I think in Euclid, is it did they say bounded by BC and A or containing or between BC and A, something like that?
It just says the rectangle contained by the 2 lines.
Right, contained by. I see. Yeah. So I guess I changed it because I thought contained by. What the hell does that mean?
Maybe
I changed it to bounded. Maybe contained by. This is
I don't think we want to repeat that because that's a very, to modern ears, that doesn't make sense. I wonder if the Greek word has a better translation than contained. I wish I could read the Greek.
Yeah, but contained bounded is what we're doing here. So cool. So this construction here is probably not super complete. So I'm going to do this again on the other side with a bigger picture. So there's some constructions here, and this is kind of important because this is the point of the proof. Otherwise, there's really nothing to do. You just draw the rectangles and you're done, right? So let me do this properly and not skip over these details. So we have a line BC, right? This B and C points there, and we have points D and E on the line, and we're going to construct a line from BF here. I'm going to construct a line here using proposition 11. In proposition 11, 1.11, now we have to say from chapter 1 because we're on book 2. So this allows us to construct a line BF, which is perpendicular or at right angles to BC. Right, and F is this here, right? We're going to do that, and we need to bring A into the picture because A was the length of that line segment, the other line segment that we wanted to be the other side of this rectangle. So we're going to cut this line at the point G using another proposition from chapter 1, which is proposition 1.3. Proposition 1.3 allows us to cut guess gives G on BF such that BG is equal to the length of A. I'm just going to write length of A. I feel uncomfortable writing BG equals A. So yeah. So now we've got this rectangle, which now we can complete the rectangle. Actually, we can use the proposition from earlier and just complete this rectangle by drawing the other two sides, either by drawing parallel lines. I guess yeah. Actually, that's what we're going to be doing. So we're going to be drawing a parallel line from G that's parallel to BC, and then we're going to draw a parallel line from C down here, have it intersect at H that's parallel to BG. So I'll make a note of this in a bit. So these are parallel, these two are parallel, right? And this is intersecting at H. And we actually want to do more of these. So I'll just draw in all of these and just make a note as to what proposition we're using to construct these parallel lines. Parallel lines here and here. And they're going to intersect the line GH at K and L. And notes down here is that the proposition 1.31, right, constructs parallel lines, well, line constructs line at a given point parallel to another line. And we can see that line, singular. We can see that's what we've done here, right? Like the line here, GH, is constructed using 1.31 as a line parallel to BC. So here, this is parallel to BC from G, right? And then we've done the same thing from C, that's parallel to BG. And then we've done the same thing to DK and EL. These are all parallel to BG, starting at points D, E, and C. Okay, so we've got these constructions, and essentially we've constructed these rectangles so that two of them, or three of them, are contained in the big one, right? Then we can use this to say that the areas sum to each other. And that's really the contents of the proof. So most of the work is in the construction itself. So let's hop over here. Okay. Is there a way to have the orb cam point at the middle two boards?
Yeah, if you just walk left a little, it'll do that. Too far.
Okay, cool, awesome. Oh, too far? Okay. Yep. Oh, awesome, nice. I think I clicked There we go. Okay, so where are we up to? We're up to proof. So the proof is actually this is something that we've talked about, but something also we probably take for granted. Let's remind ourselves. Proposition 1.34, right, tells us that the opposite sides of a parallelogram are equal. So if we go back to the previous diagram, we've constructed BG here to be equal to A, right? And so we know that the big rectangle BGHC is the product, as Dan was saying. This is a much better way of saying it. BC and BG, BGHC is really the product of BC and A. And using proposition 1.34, we can say that these are all equal, right? Because these are all opposite sides of a parallelogram, the parallelograms being these rectangles that we've constructed. And so then the diagram here really is, right? Let me just write here from the previous kind of notation. This thing here is RDE. This thing here is REC. This thing here is RBD. And the whole thing is RBC, right? Because of what we of proposition 1.34. So R, B, D, right? This is equal to BK. And R, D, E is equal to DL. So I'm just writing down what we've kind of drawn on the diagram there. R, E, C is equal to E, H. So I'm also using the convention that the two opposite corners of the rectangle, that's what we're going to call the rectangle. So this is something we've also seen before in the previous book as well. BC is equal to BH. So we see that just from construction, right? BH is the big rectangle, right? So this is the big rectangle. This BH is really equal to the sum of BK plus DL plus EH. And so if we just substitute everything else in there, we've got what we're looking for, right? So BH here is RBC. So I'm just kind of rewriting things again. And this whole thing is going to be RBD plus RDE plus REC, which is what we wanted to do. Now, there's okay. So as stated in Euclid, he does it with, subdividing the big rectangle into three parts. But I think the spirit of this, in the footnote, this is really a geometric representation of the distributive law, and the distributive law holds for an arbitrary number of terms, right? When you're doing addition and multiplication, right, you're allowed to pull that A out. You go back to the previous, maybe the first board, right? In that algebraic expression there, A times in brackets this one, right? You're not limited to three terms here, right? So to really do this right, we need to use induction. And if we use induction, I'll just kind of make a comment here as to how to turn this into an induction proof. So what we usually do with induction is that we assume that the statement here is true for an n number of terms, right? And so what you would do is that you would draw the rectangle. Maybe I'll draw it again over here with some space. So this is, I'll just reproduce the diagram here. Right. So I'm not going to label anything, right? We're just going to do this construction as we've done before, right? We're going to subdivide this rectangle into, I guess, n parts. So this is B. This is maybe B1. This is Bn. Maybe this is Bn plus 1. Maybe I should have done Bn plus 1. Maybe like this, right? So if we assume that the proposition holds for n terms, right, then we really have to, the induction step is really just summing up the area from this rectangle here, right, and this rectangle here. So if we redo the proof with induction in mind, it actually is easier. We don't have to divide it into three different rectangles. We only really have to divide it into two. And we talked about this in the last season as well. There was actually something there that used induction. We kind of just said, well, Euclid doesn't use induction, but this is how we would do it in the modern sense. So I won't go into the details, right? There's probably a few minutes left. I don't know, Dan, with proposition 2, when I looked at this, maybe I'll write this down as well before we pause for questions. So proposition 2, the algebraic identity is, so the proposition 2, the algebraic identity is that if A equals B plus C, then AB plus AC equals A squared, right? So if we use proposition 1, I know we're, probably if we do this algebraically, then it's really the same thing, right? But maybe the point is that Euclid doesn't have algebra, right? And his if you want to do it geometrically, you can't really do the factorization that I'm about to do. Just pull out the A, right? Put B plus C there, right? And then use the fact that, well, actually, yeah, this is from proposition 1, right? Right. And then, if B plus C is A, then obviously this is A squared, right? But I guess without algebra, this factorization procedure you probably can't do using the geometry, right? Which explains why proposition 2 is a proposition by itself. I don't know. Do you agree with that, Dan?
I think it's a bit of a mystery. I didn't, because I was lazy, I didn't try, but it seems like you surely must be able to deduce proposition 2 from proposition 1. Right? Yeah, it seems strange. The proof really doesn't make use of proposition 1. It's kind of making use of similar ideas. It's a little bit different. Maybe let's come at this. There's a related question that I think comes to maybe the point. So what does sum mean in Euclid exactly, right? So we've seen sums in book 1, sums of sides, sums of angles, sums of areas. Maybe let's briefly talk about each of them in turn. So, for example, Euclid was just reminding us about the proposition that the sum of two sides of a triangle is always greater than the third. Now, what does that mean? Well, I guess in Euclid's view, what that means is if you were to take those two sides and make them into a straight line, then that would have as a part the remaining side, right? Sort of the fundamental notion in the common notions is wholes and parts, and you can directly compare things with their parts, right? And somehow that's how these inequalities always work. Ultimately, right? They always work by subsuming the smaller thing as part of the larger thing and then observing that it is a part.
Right. So you have to put them next to each other so that they form something else that we understand and we can say something about it. There's no abstract notion of we add this area to that one and then we just know it because we know about numbers.
That's right, yeah. So when it comes to adding angles, I guess we always also just construct an angle that has those two angles as its parts. That's what sum means. Areas, that's tricky. I remember talking about this last time, and I forget exactly what all the subtleties were that I was thinking about, but obviously you can just take two rectangles and stick them next to each other. That's fine, but there are some parts in the later bits of Book 1 where there are more complicated figures whose areas are being thought about that aren't just rectangles, right? I forget where exactly, but I remember thinking about that. So to come back to proposition 1 here, you twice, piss off, you're in the way. So to come back to proposition 1, the sum is, I guess you construct these lines, and then, well, there's a little bit of a subtlety, which is we have to know, for example, the line dk. So we construct that line, and then we need to know that that's the intersection k when you draw that line could in principle be over on the line bg, right? Now you know that's not the case because proposition 34 says that the sides have equal length and BD doesn't have negative length, I guess, or something. So you know it has to be, etc. So then you have this figure and it has as its parts these things. So the expression that you write RBC equals the sum of those three terms in Euclid's view is this figure, right? It's the large figure with those three parts. Okay. Now, proposition 2, which I guess we'll maybe do next time or skip. The difference is that one of the things that you're multiplying with AB is kind of a part. That's the only difference, right? Like in proposition 1, the parts on which you're constructing these rectangles, you're constructing three rectangles with this line A and these other segments. they're all separated, right, next to each other. And in
Yeah.
proposition 2, there's a coincidence, and I think that's the distinction which prevents it from being just instantly, geometrically, a consequence of proposition 1. Now, when we write it down in the algebra, this coincidence isn't there, right?
Right. Yeah.
Well, maybe it is. I guess it's the common occurrence of the symbol A in both summands or something, right? Now, when we look at it in the algebra, we don't even notice this common occurrence because we just sort of, well, we do when we factor, but somehow we're able to think about it as being 2 copies of that length or something, right? But geometrically, it's like it's the 2 things, the bases of those rectangles actually having some overlap. So I think that's what's responsible for the modified proof, but I guess I would think that maybe you can just sidestep this in the first step and then apply proposition 1. It does seem like unnecessary to repeat the ideas in this way.
I'm very curious to think about all the people who have read this throughout the ages. I mean, there's got to be a lot of them because this book is hella old. what they thought about this question, right? Why do we need proposition 2?
Let's ask the...
We can't be the only ones who are like, what the hell?
No. I mean, of course it would spoil the fun to find out too easily the answer. But, you twice, is there a proof of proposition 2 of book 2 using proposition 1 directly? So actually the AI knows the footnotes in Heath's version of Euclid.
Right.
So, but I don't think there's a footnote addressing this. Yeah, I guess we'll probably stop there for questions. We won't do proposition 2 today. I'll escape that duty and start next time. Yeah, so the plan for this season is just to continue as we did last time. For those of you who didn't join in Euclid last season, we get through usually 2 propositions every week in the half-hour slot. And then, often the fun part is kind of discussing the ideas that are embedded in Euclid and how we think differently about sum and the underlying framework of ideas in Euclid is of course very different to how we think about some of this mathematics now. Different, but not necessarily more shallow, right? So despite being algebraic geometers, I'm curious if you agree with this, Kenneth, but I mean, when I started algebraic geometry, it's like, give me the algebra, man. Don't show me these stupid triangles. This like high school math. I don't want to see triangles. And that's
triangles?
Well, just like Euclidean geometry. I was sick of that after high school.
Oh, right. Yeah. I see. You mean you didn't? Yeah. So actually, when I was learning algebraic geometry, I remember asking my advisor Daniel this, different Daniel. Where's all the classical geometry, right? Do I need to know any of that for algebraic geometry? And he says no, but then, he actually knows a lot of classical geometry, and he uses it as well. And so, with classical, as in like probably 19th century kind of surface geometry, not this far back, right? I guess it was a different question, but yeah, I mean, I did have a desire to look at some concrete examples. Learning about sheaves and all the machinery of cohomology can make it look like not geometry after a while. But of course now, whenever you see cohomology, you think, okay, this is geometry. But when I was first starting, this is not what a novice sees, right?
Yeah, but I think my more mature opinion is that, I mean, algebra is great. It's a tool of great power. But often, I mean, that's true of all symbolism, right? Symbolism has great power, but it can put between you and the beating heart of the idea a lot of distance, maybe too much distance. And what's great about Euclid is that it's right on the surface, right? The idea of sum as combining shapes into bigger shapes, the people who invented measure theory drew a lot of inspiration from thinking about how area works in Euclid, for example. So, it's like behind a lot of the modern forms of mathematics are, it goes back a lot further than maybe it seems. Right.
Yeah.
Yeah. Any questions about today's propositions? Reflections on Euclid before we wrap up?
Actually, I feel like I'm cheating a bit too much with the notation. I might scale it back a bit and go back to how he says it. Yeah, as you said, we may actually lose the heart of how Euclid does things if we rely on modern notation too much. So yeah, despite what I said at the beginning.
Well, it's a tricky balancing act, right? Because of course it does help us as a modern audience a lot to have the symbolic version to hang on to. Otherwise, it's hard to organize in your mind what's going on. But yeah, and we don't. And as we were saying, I don't like this rectangle contained in two lines or whatever. So I think we find some medium there where we use modern terminology or a way of saying it and the notation without maybe losing the contrast in perspective that's offered by Euclid is part of the value of looking at it, right?
Yeah. Cool.
Okay, U-Twice is going to offer rewards. so there you go, everybody. There's prizes if you present propositions next week.
I have just a minor reflection. This is my first Euclid, and I'm very conscious of all the stuff I know that I need to let go of. And it's hard to... I can imagine how it's built up from nothing in book one, but I don't quite know. And I have an idea of what that nothing might be, or what I'm allowed to know, like just sort of pencil and compass kind of thing, nothing more, maybe. But I feel a bit like I have a gap. It's hard to know what I am not allowed to know.
Yeah,
I'm not allowed
that's
to
right.
take for granted, coming in at this point.
Yeah. I'm trying to think of the fast way of... I think taking a look at the axioms obviously is the first step, and beyond that, I mean, there was a graph up here earlier that shows you kind of what the heavily used parts are. But yeah, maybe what I would do is one of these propositions that we just made use of. Let's see, so proposition 1.34 or 111 maybe. If you go back a few of these and just see how the axioms get used, you'll get obviously the complete answer to your question is just to read all of book one, but you can get a lot of the value from that, a sense of what you're allowed to do and what not, just by tracing back a few of those propositions some of the way, and you'll get an intuition for... I mean, there's kind of there's workhorses in book one that will use more than other things, and if you get a sense of what they are, then that probably is 50% of the picture.